So, good morning. We'll start the next part of this chapter number 9. In last lecture, we have seen the block diagram of JPEG encoder. Okay, and before that, we have studied the three important observations. Okay, and based on that three important observations, this image compression standards are decided. Okay, so in last lecture we have studied this block diagram, like when you take the input image, okay, if it is color image, okay, if it is grayscale image, okay, divide this image into 8 by 8 block, okay, and then take DCT of each block, okay. After that you have to do the quantization, okay, and then after quantization, okay, these DC values, whatever you get in the DCT domain, will be coded first with DPCM, that is differential pulse code modulation technique, and the AC coefficients which are there will be coded with run length coding. Okay, and after that again entropy based coding like as Huffman coding is applied to both AC as well as DC, and finally you will get the compressed image. Okay. In case of color image, first thing is that you have to convert that one into YIQ or YUV model, and then procedure will be same for that one. Okay. So we'll see the next part of that one in detail. Okay. So main steps in JPEG compression. In this lecture, we are going to study all those steps in detail. Okay. So main steps in JPEG compressions are, first thing is that you have to convert, if it is color image, convert that RGB into YIQ or YUV subspace. Okay. After that, divide this image into 8 by 8 non-overlapping blocks, and then take the DCT of each block. Okay. After that, do the quantization, and then once quantization is done, do the zigzag ordering, and then run length encoding for AC component, and then this DPCM for DC component, and after that for both AC and DC apply the entropy based coding. Okay. So we'll see steps one by one in detail. Okay. So here each image is divided into 8 by 8 block. Okay. Why 8 by 8 block? I think I had told you in last lecture, because see, if you increase the size of block, so for example 8 by 8 instead of 8 by 8, if it is 16 by 16, okay, definitely encoding low frequency component will be efficient, but at the same time computation complexity will increase. So this JPEG committee decided that this 8 by 8 size is the optimal size. That's why this 8 by 8 image is divided into 8 by 8 block. Okay. After that, the 2D DCT is applied to each block image Fij with output being the DCT coefficient of f of UP. Means once your image is there, okay, so this image is first divided into 8 by 8, and for each block, okay, DCT is applied, okay, 2D DCT, okay, so if this is f of x comma y is the original image, after that, okay, after this operation of two-dimensional DCT, you will get the coefficient f of u comma v, means image will be represented in DCT domain, okay, where coordinates are u and v, whereas in original image, okay, the spatial coordinates were x and y. Number of DCT coefficients are equal to your original image size, since your DCT is an orthogonal transform. Okay, so there is no redundancy and so on. Okay. Now, why this step is done? Why transform is taken? The main reason is to decorrelate the data. Now, what is by correlation? There is a similarity, and okay, if there is similarity, okay, with the help of this DCT, okay, you can decorrelate that data. Means, so for example, if there is a similarity of that one, definitely the DC component will be, or low frequency will be more, so DC component will be larger, and then AC component will be minimum. So after taking the DCT, okay, coefficient will be decorrelated, and the compression of that decorrelated coefficient will be much more efficient as compared to the correlated one. Okay. So using block, however, has the effect of isolating each block from its neighboring context. Okay, this is why JPEG images look as a blocky, okay, or choppy when high compression ratio is specified by this one. Okay, so if compression ratio is increased, because compression ratio is decided by the user, how much compression is needed. So if you definitely, if you put the high compression ratio, what will happen? Image, you are going to lose a lot of information, and if you are going to lose a lot of information, then what will happen? The quality of the image will not be good. Okay, so there will be blocking artifacts in the image. So if compression ratio is less, definitely your quality of the image will be good, but if compression ratio is high specified, then you'll get the blocking artifact in the image. Okay, after that, the quantization. Okay, next step, see, once you get this one DCT domain image, okay, the next step of this one is quantization. Okay, so quantization, what is quantization? See, f of uv represent the DCT coefficient, okay, and q of uv is the quantization matrix entry. Okay, q of uv is the quantization matrix entry. So this quantization matrix entry is also predefined. Okay, who has defined this one? See, what should be the quantization step for low frequency? What should be the quantization step for high frequency? Now, what was our observation? See, if you lose high frequency information, are you going to detect that one? No. If you lose the high frequency information, you are not going to detect. Human being does not detect the change, but if you lose the low frequency information, human being can detect the change. So the quantization step for low frequency in case of this one grayscale image, quantization step for low frequency is smaller, and quantization step for high frequency is larger. Okay, so by using a psychovisual study, okay, this committee has decided what should be the quantization step for each frequency. Okay, for each frequency, what should be the quantization step? So that is decided by the JPEG committee. So you have the standard quantization table. So based on that one, this coefficients which you have got, DCT coefficient, will be quantized, okay, or rounded off to the nearest value. Okay, so Q of UV are the entries of quantization table. These are the standard quantization table in JPEG. Okay, and then after quantization, whatever the image you are going to get, okay, see, after quantization, whatever the image you are going to get, okay, it will be represented by, okay, f cap uv. Okay, see that your original image is f of x comma y. Okay, after DCT, okay, it is represented as f of u comma v. So this is in frequency domain. After frequency domain, what you are doing? Each coefficient is quantized. So you are mapping to the lower bits. Okay, by using less number of bits, you are going to represent it. Okay, so quantization. After quantization, this image, whatever you are going to get, okay, quantized image will be represented by f cap u comma v. Okay, now, so represent the quantized DC coefficient which JPEG will use in succeeding. After that, what will be there? After quantization, encoding will be there. Now encoding, okay, we'll see later on how encoding is done, but look, just see that what are the quantization steps. Basically quantization step is the main source of loss because you are going to lose some information in that. And the entries of Q, U, comma V, that is the quantization table, entries of quantization table tend to have larger values towards the lower right corner. See that if you see the 8 by 8 image, so total number of pixels will be, see 8 by 8, so total number of pixels will be 64. After taking DCT to DCT of this one, what you'll get? You'll get again 8 by 8 coefficients, so total coefficients are again 64. So this is U equal to 0, V equal to 0, this is V equal to 7, U equal to 7. So here you will get U and V equal to 7. So this part is basically of low frequency and then this part will be of high frequency and the remaining will be the mid frequency. Okay. Now see that what is the first statement here? The entries of QUV tend to have larger values toward the right corner, means entries of this quantization matrix is having larger value toward the right corner. Okay, toward the right lower corner. This is the right lower corner. So what is the frequency of this right lower corner? High or low? High. So this high frequency they have taken higher or larger value of quantization step. Why? You have to correlate that one with our observation that even if you lose the high frequency information, human being does not detect that one. Okay, that's why quantization values at the right corner are having high values. So this aim to introduce the more loss at the higher spatial frequency and a practice supported by observation 1 and 2. Okay. Now this table 9.1, okay, and 9.2 next table show that the default values of Q of U comma V values obtained from the psychophysical studies with the goal of maximizing compression ratio. What is the goal? To maximize the compression ratio while minimizing perceptual loss of in JPEG images. So with the help of that one you can maximize the compression ratio. At the same time you are not going to lose the much information. Okay. Now see that this is the luminance quantization table and this is the chrominance quantization table. What is by luminance quantization table? Grayscale intensity basically. Okay, and this is the chrominance means color information quantization table. This is 8 by 8. See that what is the value of quantization step toward this one? It is low, whereas towards the right lower right corner, okay, these values are higher. So these values are standard values of quantization. Okay, these are the standard values of quantization. Who has decided all those values? JPEG committee. Okay, based on what? Based on the observation 1 and 2. Okay, so in JPEG compression you have to use these values for quantization steps. Okay, so when you are basically quantizing the DC component, okay, so for example, if your DC component is having value equal to 512, okay, after quantization, what will be the value of this one? See, you are mapping with the lower value. Quantization is the step you are mapping with higher value with the lower value. Okay, what is the now lower value here? In quantization table, this is the luminance quantization table. Okay, so if DC component is 512, okay, after quantization, what will be the value of this? It will be 16 or something different. See, quantization step is 16, that is delta value is 16, means you have to divide this DC value by quantization step. So 512 divided by 16, how much it is coming? 32. Is that correct? So after quantization, whatever the image you are going to get, this value will be equal to 32. Earlier, what was that value? 512. After quantization, it is 32. Okay, how you got this one? We got from the standard quantization table. We use that to 16 as a quantization step for quantizing the value. Okay, same thing is there for the chrominance component. Okay, so you got f cap u comma v after quantization. Okay, after that, see that, for example, okay, this is the portion which we have taken here, the square one. Okay, now in that square portion, what do you think that? Whether spatial frequency is higher or lower? This is a background side, so most of the pixel intensities are same, so spatial frequency will be low. If spatial frequency is low, then after taking DCT, what you'll get? You'll get higher value of low frequency and lower value of high frequency. So for example, this is the portion of 8 by 8 and these are the values of that one. Okay, like 200, 202, 189 and so on. Last one is 186. So this is your original image, 8 by 8. We have taken this portion of the image. Now after taking the DCT of this image, what you got? You got the values of f of u comma v as a 0, 0 will be 512. Then u is 0, v is 1. Okay, 65 u minus 12 and so on. So what is this? F of 7 comma 7. U is 7, v is 7. So high frequency is 0. Or most of the high frequency component are negligible as compared to this one. Now this is the basically you got DCT, two-dimensional DCT of original image. What is next step? Quantization. And for that, what you have to do? You have to use the standard quantization table entries for this one. So after quantization, okay, what you got? You got the value of this DCT coefficient like this, 32, 6, minus 1. You have to take the nearest value. Suppose for example, after taking this one, dividing, suppose for example, it was 513 by 16. So definitely it will come 32 point something. So you round off it to the nearest value. Okay, so if it is less than 32.5, okay, round out it to the 32. If it is greater than that one, round up it to the 33. So like that way, you got this one. So this is the output of quantizer. Now what you got here? Most of the high frequency components are 0, whereas the higher value of low frequency component. Okay, now this is the image after taking inverse DCT. Okay, just we are seeing how much is the loss in that. Okay, so this is the quantized image. Then if you take the inverse DCT of this one, you got this one. Okay, after that, inverse quantization of this one, you'll get this one, and then this is the inverse quantization, and if you take the inverse DCT of this one, you got this image. See that? This is the quantized image. After inverse quantization, how do you do the inverse quantization? Instead of dividing, you are going to multiply it. So you got this one. Okay, so this is the f tilde u comma v is the inverse quantized image, and then if you take the inverse DCT to DCT of this image, you got this image. Okay, now this is the reconstructed image. This is the reconstructed image. Now we have original image f of I comma j. Now this is the reconstructed image f tilde I comma j. Now how much is the difference between reconstructed image and original image? And that is nothing but f of I comma j minus f tilde I comma j. So this is the difference I comma j equal to f of I comma j minus f tilde I. So this is the error between original image and the reconstructed image. Okay, I hope that it is clear. 3 steps. Which are those 3 steps? First thing is that you have taken DCT, 2D DCT, after that quantization, then okay, inverse quantization will not be there in encoder, inverse quantization will be there in the decoder, inverse DCT will be there in the decoder, but we have just checked the intermediate result whether we are getting the correct one or not. Now what is your observation from this image, reconstructed image? See what portion we have considered in this example? Basically the portion of the image where spatial frequency is low. So after that, see what we have done, okay, most of the high frequency components are 0, okay, and then after reconstructing this one image, you got very less difference between original image and, see that means only one grayscale value. This is the grayscale value difference between original one and earlier one. It was 200, now it is 199. Earlier one it was, suppose for example 1 or 202, it is now 196. So you got 6 and so on. So this as compared to 200 or 206, okay, these values are really negligible. So difference is negligible. Now we'll consider another example of the same image. Okay, see that this is the JPEG compression for the smooth image block where spatial frequency is less. Now see that. Oh, sorry. Oh, actually this block should have been here only. Okay, hair part. Okay, so at hair part, what is the spatial frequency? Higher. Okay, rate of change of pixel intensity is higher in that case. Now, so for example, this is the pixel values of that portion. Instead of that square, you consider this is the square. Okay, so these are the pixel values after taking 2-dimensional DCT. What do you got? See, in earlier case you got maximum value of low frequency whereas minimum value of high frequency, but now the portion which we have considered of hair of that lena, okay, contains high spatial frequency or rate of change of pixel intensity is high. In that case, okay, what is reflected here? The high frequency components are also there in that portion. Okay, low frequency earlier, what was that low frequency value? 512, now it is minus 80. Okay, so this is the basically 2-dimensional DCT value of high frequency spatial frequency area. Now after quantization, okay, you got this value, okay, by using standard quantization table. Again after inverse quantization you got this value. After inverse DCT you got this reconstructed image. Now you have original image and this is the reconstructed image. What is the difference between the original image and reconstructed image is this one. Now if you look the earlier reconstructed image and this textural reconstructed image, what do you observe from this one? Error is more. Error is more because high frequency contents are more in that case. See that these values are nothing but the error values. Okay. So these are the 3 steps. Now run length encoding. When it is done, see you have this original image, divide this original image into 8 by 8 block. Then for each 8 by 8 block, what you are doing? Take the 2-dimensional DCT. So for each 8 by 8 block you have one DC component and how many AC component? see that for each 8 by 8, suppose this is the 8 by 8, you are going to get this DCT, two-dimensional DCT. Now this 8 by 8, again 8 by 8. Okay, so this is 1, this is 8, this is 1, this is 8. Okay, so how many DCT coefficients you got? 64. Out of that, this will be DC component of that DCT, and this is first AC component, that is AC1, this is 7th AC component, AC7, this is 63rd AC component, AC 63. So how many in total AC components are there? 63. How many DC components are there? 1. Okay. Now, so for example, if you have an image of 128 by 128, okay, if you have an image of 128 by 128, how many non-overlapping 8 by 8 blocks will be there? See that this will be 128, this will be 128, this will be 64, then 64, then this will be 32, 32, then 16, okay, and 16, and then 8 by 8. So how many such components will be there? 256. See, in first row how many are there? 16 na? And such kind of columns are also 16. So 16 by 16 will be equal to 256. Okay, so 256 8 by 8 blocks are there. So after taking DCT of each block, okay, how many DC component will get and how many AC component you will get? You will get 256 DC component and 128 by 128 minus 256, that many DC component, AC components will be there. Okay, so now here we are going to use run length encoding for AC component and DPCM for DC component. Now in DC component, see, basically AC component you are going to consider only a block of 8 by 8. How many AC component you are going to consider? 63. In 8 by 8 block, how many AC components are there? 63. But while coding DC component, what you are going to do? You are considering the entire image, DC component of entire image. For 128 by 128 image, how many DC components are there? 256. So simultaneously all those 256 components will be considered for DPCM, whereas for encoding AC component, only AC component of 8 by 8 block, that is 63 components are considered. So here only 63 components are considered. Now, here zigzag encoding is done. Scanning is done in zigzag mode. Why zigzag mode? Why not sequential mode? Because run length encoding will be more efficient if you go with this one. What will happen? Suppose for example, if you go sequentially, definitely this will be having the low frequency component, this will be having low frequency component. So basically this portion is a low frequency, whereas this portion is of high frequency. And you know that most of the images, high frequency coefficients, or after quantization, most of the coefficients are 0. So suppose for example, see, when you come to this point, you are coding, then like this way, again you are coming back one, and like that. So for example, the more prominent coefficients are in this region of that DCT. Rest of the coefficients are 0. So for example, after this block or after this coefficient, rest of the coefficients are 0. So what you are going to write? 0 at the rate, how many times? The number of zeros. So you are going to terminate coding there only. So it will be more efficient if you use the zigzag encoding rather than sequential encoding, sequential scanning. Okay, zigzag scanning is used. Is it clear? Okay. So to make the most likely to hit a long run of zeros, a zigzag scan is used to turn the 8 by 8 matrix of f of u v into 64 vectors. Now DPCM, that is differential pulse code modulation technique on DC coefficient. So the DC coefficients are encoded separately from the AC ones by using differential pulse code modulation method. Okay. Now for example, see that why this differential, all those DC values are considered. Why separately it is done? What is the reason for taking this DC component separately of each block? The assumption is that, or observation is that, most of the DC values of consecutive blocks are same. Similar values are there. Okay. So difference between this DC value and this DC value is negligible. So coding will be more efficient if you take the DPCM. So that is the reason. So most of the neighboring 8 by 8 blocks are having same value of DC coefficient. So DPCM is used for efficiently coding the DC values. So if the DC, so for example, now this is 8 by 8 block. Okay, this is another 8 by 8 block, next one, and so on. So like that way, for example, first 5 8 by 8 blocks are having DC values like 150, 155, 149, 152 and 144. Okay, what will be the output of this DPCM? Okay, you are going to put this as like this one, then difference between the next one and the first one. What is next value? 155 minus 150, so that is giving you 5. Then next value will be 149 minus 155. What you got? Minus 6. Then 152 minus 149, you got 3. Then 144 minus 152, you got minus 8. Okay, so like assuming di is equal to dci plus 1 minus dci, and d0 will be equal to what? Your original dc 0. So first block DC value will be DC 0. So like that way, differential code, you got these values of this one. Okay, why? See that most of the values of this neighboring 8 by 8 block DC values are more or less similar, 150, 155, 149 and so on. Okay, so this difference is less, and then it will be more efficiently coded by using DPCM. Okay, after that, see, your DC coefficients are encoded by using DPCM first, and all AC components of every 8 by 8 block is encoded by using run length encoding. Now you have this DC coefficient coded by using DPCM and AC coefficient coded by using run length encoding. Now both AC as well as DC are further encoded to increase the compression ratio by using entropy based coding, that is nothing but the Huffman coding. Okay, so the DC and AC coefficients finally undergo the entropy coding step to gain a possible further compression. Okay, so use the DC as an example. Each DPCM coded DC coefficient is represented by size amplitude, where size indicates how many bits are needed for representing the coefficient, and amplitude the actual number of bits. In the example, we are using codes like 150, 5, minus 6, 3 and minus 8 will turn out to be like this. Okay. Now size is, see that 8 is nothing but, okay, 8 and then 3, so like that one. Then size is Huffman coded, since smaller size occurs much often and amplitude is not Huffman coded, its value can change widely, so Huffman coding has no appreciable benefit in that case. So this is the size of this one. Okay, if size is 1 means you have a value ranging from -1 to 1. If size is 2, you have bits value ranging from -3 to +3, including 0, okay, 3 and so on. So if number of bits are 10, so you can encode, okay, the size of that one will be equal to, amplitude can be encoded from -1023 to +1023. Okay, now this is the example of this. If is This X is the 8 by 8 block. After applying two-dimensional density of this one, you got this one. Then what is next step? Quantization. So use the standard quantization table. So you got this one. Then zigzag ordering. Okay, you got run length encoding. Okay, after that Huffman encode. Okay, and so on. Okay, so like that way encoding will be done and you will get the compressed image. So in summary, what do you do? Divide image into 8 by 8 block, then or each 8 by 8 block, find out the two-dimensional DCT, okay, then after that do the quantization, and after that, after quantization, DC component is encoded separately by using DPCM, AC component use zigzag scanning and use run length encoding, and both AC and DC are further encoded by using Huffman coding. So you got the encoded or compressed image. Now, what are the different 4 commonly used modes in JPEG? Okay, so there are 4 different commonly used modes. One is the sequential mode, another one is the progressive mode, third one is the hierarchical mode, and lossless mode. Okay, so the sequential mode is the default JPEG mode implicitly assumed in the discussion so far. Means basically, okay, when you are doing the encoding, okay, you are doing it sequentially. So like for example in television engineering, okay, how scanning is done? Sequential scanning is done. You start from the top left, okay, scan first row, again come to the second and scan second row, and so like that way up to what? Up to the last. So every value is scanned in order. So that is called as the sequential mode. Okay, means every pixel is basically is encoded and then it will be sent in sequential manner. Okay. Now in progressive mode, what is done? In progressive scanning in television engineering, what is done? Basically, to make it fast, okay, you are scanning odd lines first. First line, then third line, then fifth line, seventh line, and so like that way. And in the second phase, even line scans will be done. So first odd part will be sent. So you have low resolution image at the receiver side, and if receiver is happy or if user is happy with low resolution, he will not wait for the next scan. But if he in more higher resolution image, so then he will wait for the next incoming this one information. Are you getting or not? Okay, so the default JPEG mode is sequential mode. Assume that discussion is over. So each gray level image or color image component is encoded, okay, in a single left to right. Okay, you are scanning from left to right and top to bottom. You are ending at where? Right bottom point. Okay, so we'll see this one, progressive mode first. Okay, so progressive JPEG delivers low quality version. Okay, another one, progressive mode is, as I told you that it will scan from left to right, okay, left to right and top to bottom, but it will not scan all the lines. It will scan alternate line, means first line, then second line will be not scanned, then third line, and so on. So what you'll get? You'll get the approximate picture na? At the receiver side. If receiver is, user is happy with that,